Okay, question 6. We have a fission reaction, and first of all we need to state what is meant by the binding energy of a nucleus. So that's a standard one. You got to know it's the energy required to completely separate a nucleus into its nucleons. So let's just quickly write that down. So it's the energy required to completely separate a nucleus into its nucleons, the protons and the neutrons that make up the nucleus. Okay, outline why quantities such as atomic mass and nuclear binding energy are expressed in non-SI units. So that's because, of course, if we measure atomic masses in kilograms, we get really small numbers and we have to carry around very large negative powers of 10. So it's more convenient to just introduce some new units that are easier to work with. So this is simply due to the inconvenience of working with very small numbers, say. Or we can say that mass and energy at the nuclear level are have extremely small values. Using kg, joules, etc. Okay. Show that the energy released is about 180 mega electron volts. Okay, so we have to look at the reaction, and they've given us the binding energy per nucleon. Okay, don't forget that for the various nuclides. Okay, so remember that we're going from something that is less stable to something that is more stable. So it's sort of like the binding energy increases on average as we move to the right in this reaction. So we're going to have a larger total binding energy on the right hand side compared to the left hand side. So what I'm going to do, I'm going to calculate the total binding energy on the right hand side and subtract from that the total binding energy on the left hand side. So on the right hand side we can see that we have the xenon. We have 140 nucleons in a xenon nucleus, and we have to multiply by 8.29 MeVs, and then we have to add that to 94 strontium nucleons times average binding energy per nucleon for that. Okay, and the neutrons, of course, are just individual nucleons, no binding energy. And then the left-hand side is just the uranium, 235 times 7.59, right? And then we're going to subtract those two. So basically 140 times 8.29 plus 94 times 8.59 minus 235 times 7.59. And that's all going to come out in MeVs, and we get around 184 MeVs if I plug that in correctly, and that is around 180. Okay, then we are now looking at a nuclear power station. So let's assume every fission reaction gives rise to 180 MeVs, like we just calculated, and then we have to estimate the specific energy, right? And we have to give it in units of joules per kilogram. That's the SI unit for specific energy. Okay, so basically we know that we get 180 MeVs of energy. We can convert that to joules, divided by, and then we just need the mass of one uranium-235 nucleus. So that should be easy enough. So we have 180 million EVs, and one EV is 1.6 times 10 to the negative 19 joule. And then what is the mass of one uranium nucleus? Well, we have 235 nucleons. They're each around 1 U. They have a mass of 1 U. And let's convert that to kilograms. 1.66 times 10 to the negative 27 kg. You can look that up in your data booklet. And if you plug that in on your calculator, you get 7.4 times 10 to the 13 joules per kilogram. Specific energy. Okay. And that's, by the way, remember, a very large number compared to many other types of fuel, for instance, fossil fuels. So, yeah. Then the power station has a useful power output of 1.2 gigawatts, but an efficiency of only 36%. So remember, efficiency, use the Greek letter eta for that. Definition is the useful output over the total input. We have the useful power output. We know the efficiency. We can work out the total input because we want to determine the mass that results in a total input. So the total power input is, okay, you can see that's the useful output divided by the efficiency. And there you get like 3.33 ... 10 to the 9, and this is joules per second, right? So watts, 3.3 billion watts goes in, and then, you know, roughly 1/3 of that is the useful power output. But how much uranium do we need to break apart every day in order to get that power? So this is, you know, joules per second. And before we just calculated the joules per kilogram. So I can get kilogram per second by doing the following. I can take my joules per second. And if I divide that by how many joules we get per kilogram, which is, which was what we had before, and that was 7.4, 10 to the 13 joules per kilogram. Okay, then we're going to get kilograms per second. As you can see, these units, they become kilograms per second. So we know how much mass I need to convert every second, but we don't want every second, we want the mass per day. So I need to convert seconds to days, and we know that there are 24 hours times 3,600 seconds in a day. So now the seconds are going to cancel out. We're going to get kilograms per day. And if you plug all that into your calculator, you get around 3.9 kg. So around 4 kg is the mass of uranium that undergoes fission in one day. Okay, so the specific energy of a fossil fuel is that amount of joules per kilogram. So mega, that's like 10 to the 6, right? 10 to the 6 joules per kilogram. You know, uranium was 10 to the 13 joules per kilogram. So much higher specific energy for nuclear fuel. And that is one advantage compared with fossil fuels, that we have a much higher specific energy, which means we need much less fuel to achieve the same power, right? So to get the same power, we need much less fuel. So much less nuclear fuel is needed to achieve the same power. Okay, so strontium is one of the waste products. It's radioactive. Okay, so now this question moves into a radioactivity question. Undergoes beta minus, and we know beta minus is an electron, right? So we have a nice little electron over there and an anti-electron neutrino. And then we have to write down the proton number of nuclide X. Well, we know because it's a beta minus, the electron carries a charge of -1, then the proton number of X has to be 39, right? Because we need to have the charge number, the proton number, has to balance out on both sides there. Okay, now we know the antineutrino has 0, 0, so we also know X has a nucleon number that is 94, right? Mass number. Okay, that's easy. Don't get those wrong. And then here we have the exponentially decaying curve for the mass of strontium. Okay, so it's decaying over time. State the half-life. Okay, well, we can read that off. We start off with 1 kilogram. How long does it take for half the sample to decay? That takes 75 seconds, as we can see. Easy to read off. Doesn't get easier than that. Calculate the mass remaining after 10 minutes. So, I mean, you could go ahead and use the exponential decay law if you want to. You have to maybe work out the decay constant first. So let me just remind you that you can, of course, use this, the radioactive decay law, but we can also rewrite that in this way. So if the decay constant, remember, is ln2 over the half-life, something you should be able to derive yourself, and if you sort of plug that in, or if you plug that in and then sort of simplify, then you get this version of the decay law, which is sometimes a bit easier to use. And here you can see we can just plug in 10 minutes and work it out straight away. So I'm going to do that. So after 10 minutes we have, and the initial mass was 1 kilogram times 1/2 to the power, and then we're looking at 10 minutes, but we need to convert it to seconds, divided by the half-life, 75 seconds, and yeah, it turns out that that's just 8 half-lives. So we just plug that into our calculator and we get around 3.9 grams. Okay, so first you get it in kilograms, it's 0.0039 kilograms. Yeah, there you go. Relatively straightforward question.